we are on section 6.4, Fundamental Theorem of Calculus. Now, we have actually already covered the two parts of Fundamental Theorem of Calculus, and those pieces of information are up on the board now. So the key parts that I want you to have in your notes are simply FGC Part 1 and FGC Part 2. So what you need to be familiar with and able to work with would be this. And this. Oh, no, that's probably another number. You can ask them. Okay, so it's interesting, in some books they refer to this as Fundamental Theorem Part 1 and this is Part 2, depends on which proof they use to lead them to these theorems. Okay, so if we look at the Fundamental Theorem Part 1, this is what you were working with in your lab, and we are taking the derivative with respect to x of some integral from a constant. Please remember that a is a constant, to x of f of t dt. And we went through this process, and it was included in our last video, and it shows that it will come out as if the derivative undoes the definite integral, and we are left with f of x. Okay? All right, so an example of that would be if we were doing something like d dx, the derivative with respect to x, of the definite integral from 2 to x of the cube root of sine t plus cosine t. Okay? So you're looking at that, and if you wanted to do it step by step, you would have to be able to take the antiderivative of the cube root of sine t plus cosine t. Do we know how to do that? No, we do not. So, what we will use is the theorem that we developed last class that says if I take the derivative with respect to x of this, it will come out to be f of x. So, the answer to this derivative should be a function of x, and what function should it be? Cube root of sine x plus cosine x. Done. It is this function evaluated at x. Okay? And then what happened when, instead of x, we had a function of x, the derivative with respect to x of the integral from 0 to 3x squared of tangent t plus t squared. So what happens now? So it is evaluated at 3x squared, so we get tangent of 3x squared plus what? 3x squared squared, but there's more. We need our chain rule. And applying a chain rule means that I'll multiply by what? The derivative of the inside, which is this. So times what? 6x. Good. Okay? So you should have run into this on the lab, and you'll see more of that on the homework tonight. And then the Fundamental Theorem Part 2 was just giving us a process to find area under curves. Because when we see a definite integral from a to b, f of x dx, we know we are finding the area under that curve. And what does the capital F mean? You take the antiderivative, you evaluate it at b, the antiderivative evaluated at a, and then you subtract. All right? So, all I have for you today is a whole bunch of examples. They come from places other than your book. So your book is another set of good examples for you. But I wanted to hit some of the trickier versions of these definite integrals for the rules that we know right now. So what I want to do is I'll put up about 4 at a time, and you and your partners will work on those 4, ask questions as you need to, and then we'll get our solutions up. Then we move on. All right? The only antiderivative rule that we have so far is what? What is the only way that we know how to take an antiderivative right now? Very nice. So if I'm asked to take the antiderivative, so if the integral sign is given without upper and lower limits, that's just saying take the antiderivative of x to the n dx. Chad, what was it?
X raised to n plus 1 over n
Plus?
Oh, plus 2.
Good. Okay. With the definite integral, we wouldn't need the plus b, but on this one we would. All right. So on all of these, the first one is very basic. Keep your constants out in front and integrate things that are added and subtracted. Now, before you start writing anything, please note, with integration, there is no product rule, there is no quotient rule, and there is no chain rule. So if it looks like something that we would have used quotient rule or product rule or chain rule on when we were taking derivatives, that means you're going to need to rewrite it somehow so that we can use our only rule that we have right now, which is the power rule. So you need to change the look so you can apply power rule. All right, that's going to become important in B and C. All right, so give it a try. Try to get your desk. I'm going to stop you at 50. So get through as many as you can, please. All right, so we have 4 examples. And on our next slide, we have the solutions. So you can pause here, try them yourself, and take a look at the solutions on the next page. So I will go over there. So here are the solutions to A through D. A was a very straightforward definite integral. B, we talked about in class, the need to change the look because there is no product rule or quotient rule or chain rule for integrals. So we cannot integrate this in its current form with the techniques that we have so far. So we rewrite the square root of t as t to the 1/2, and we distribute it through t minus 2. So we get t to the 3/2 minus 2t to the 1/2 dt. Then we can integrate each of these individually because they're being subtracted. And we get t to the 5/2 over 5/2, which you'll often see written as t to the 5/2 times 2/5, minus 2 times t to the 3/2 over 3/2, which is equal to 4/3 t to the 3/2. We evaluate these at 0 and at 4, and we subtract to get negative 32/15. Letter C also requires a rewrite. And when you see an integral that looks like this, what we can do is actually break it up into 3 fractions and divide each of the top terms by the w squared. So the rewrite would look like this. Definite integral from 1 to 2 of 2w cubed minus 1 over w plus 3w to the negative 2 dw. And we'll integrate each of these. Now, the middle term is the one that looks different. We cannot apply power rule to w to the negative 1 because we would get w to the 0 over 0, which would be undefined. So we have to recall, what did I take the derivative of to get 1 over w as my answer? And if you recall, it was the natural log. And one thing I forgot to mention in class is the antiderivative of 1 over w is the natural log of the absolute value of w, because we need to make sure we are not taking the log of a negative value. We have to keep that domain restriction. So that's why you'll always see the natural log of the absolute value of the expression in your solution. And so then we take the antiderivative of 3w to the negative 2, which would be 3w to the negative 1 over negative 1. And we have this form of our antiderivative to be evaluated between 1 and 2. Plug in 2, plug in 1, and subtract. And then finally, the definite integral from 25 to negative 10 of dr. We need to remember that that's not just dr, it is 1 dr. So we have to ask ourselves, what did I start with to get 1 as my derivative? And I must have started with r. So we get r evaluated between 25 and 10. The 10 goes in first. Then we evaluate r at 25, and we subtract to get negative 35. Okay. So the next set of examples also touch on some common errors. So you can pause the video and try these on your own, or you can go ahead to the next page to see the solutions. I'm just going to hit the highlights on these. So for letter A, we just needed to rewrite 6 times the cube root of x squared as 6x to the 2/3. Then we could apply power rule to 4x and 6x to the 2/3, which is going on here. Remember, to do the power rule, we do x to the n plus 1. So that's 2/3 plus 3/3 is 5/3 over n plus 1, which is 5/3. We evaluate this between 0 and 1, plug in 1, subtracting, plug in 0. We get negative 8/5. Letter B, when we take the antiderivatives or the definite integrals involving trig functions, again you have to ask yourself, what did I start with to get, in this case, 2 sine theta as my derivative? And I must have started with negative 2 cosine theta. And then what did I start with to get negative 5 cosine theta as my derivative? Well, I must have started with negative 5 sine theta. So here is our antiderivative. We'll evaluate it between 0 and pi-thirds, which means we plug in pi-thirds first. And we plug in 0 and we subtract to get our solution here. Okay. Letter C. This one, as I said in class, was easier than it looks. 2 secant z tangent z. It's written as a product, but we also have to realize, what did we start with to get secant z tangent z as our derivative? Well, we started with secant, because the derivative of secant is secant tangent. So the antiderivative of our integrand here is 5z minus 2 secant z, evaluated between pi-6 and pi-4. So we'll plug in pi-4 first, and then pi-6 and do our subtraction. To help yourself, remember that secant is equal to 1 over cosine to help you figure out what the secant of pi-4 and the secant of pi-6 is. All right, letter D also requires a rewrite. And we have the definite integral from negative 20 to negative 1. We'll rewrite 3 over e to the negative z as 3e to the z. And we'll rewrite 1 over 3z as 1/3 times z to the negative 1, or 1 over z, dz. So when we apply our power rules, remember the derivative of e to the z is e to the z, so the antiderivative of e to the z is also e to the z. So our antiderivative is here, 3e to the z minus 1/3 times the natural log of the absolute value of z, because that's the integral of 1 over z. There's that absolute value again that we must remember, to be evaluated between negative 20 and negative 1. So we plug in negative 1 first, and then negative 20, and you can leave your answer just like this. Remember, any form of the correct answer is correct for a free response. Finally, letter E, which we did not get to in either of the classes. If we look at this one, we have one term that is causing a problem that I didn't even notice when I looked at it in class, and that is this term right here on this interval. 1 over t is undefined at 0. So we are not going to be able to integrate over the interval from -2 to 3. And as stated just below this, if any part of the integral can't be done, then we cannot integrate this definite integral. And we would have no solution is able to be found in this case. All right. We took a look at this one in class as well, the piecewise function. And the key to integrating with piecewise functions is to make sure you are integrating in the proper branch. In letter A, we're integrating from 10 to 22. Well, that is all in the x greater than 1 branch, so we'll be integrating 6 for our f of x. And if we look at our next page, solutions, we're just integrating from 10 to 22 of 6 dx. The antiderivative of 6 is 6x, evaluated between 10 and 22. Plug in the 22, plug in the 10, and subtract. For the second part, we are asked to integrate from -2 to 3. Well, that crosses over the break in our two branches for our piecewise function. So we can use our integral properties to break up our integral as well. So we can integrate from -2 to 1 of 3x squared. And then from 1 to 3, we can use the proper branch, which would be 6. So looking at our solution, that's what we did here. And now we'll plug in the proper functions for f of x. From -2 to 1, we would use the 3x squared branch because that is defined when x is less than 1. And then from 1 to 3, we would use 6 dx. Take the antiderivative of each. Antiderivative of 3x squared is x cubed. Antiderivative of 6 is 6x. And then we'll evaluate it, the x cubed from -2 to 1, and the 6x from 1 to 3 to get our solution of 21. Let's just make sure we understand why the antiderivative of 3x squared is x cubed. The 3 is out in front. You leave that out in front as a constant. The antiderivative of x squared is x cubed over 3, and our 3's cancel, leaving us simply with x cubed. All right. I believe the last one we were able to do in class was the definite integral from 0 to 3 of the absolute value of 3t minus 5. So the helpful hint for this integral is there's a couple of things we can do. The first is we can use the definition of absolute value, which we have right here. The absolute value of x is defined to be x if x is greater than or equal to 0, and negative x if x is less than 0. And the reason we branch off at 0 is because that is where the vertex of our absolute value graph is, and it is where the function equals 0. If you recall, absolute value looks like this. And at x equals 0 is where the function equals 0 and where our vertex is. So the key when you're integrating these is to find where the function that's inside the absolute value will equal 0. And another thing to think of when you see an integral with an absolute value, anytime we are asked to integrate or differentiate the absolute value, we have to remember we have to do something different because there's no set rule for integrating or differentiating absolute value. So I want to know where the vertex is for the absolute value of 3t minus 5. Well, to do that, I want to see where the argument inside 3t minus 5 equals 0. And when we solve that, we get t equals 5/3. So this function, the absolute value of 3t minus 5, looks like the positive of 3t minus 5 when t is greater than 5/3, and the negative of 3t minus 5 when t is less than 5/3. So the graph looks like this. And if I want to integrate from 0 to 3 of this function, then I am integrating from here to here and finding the area of these two triangles. So, this part of our absolute value curve is based on the definition of absolute value that we had over here, is negative of 3t minus 5. And this one is the equation of that part is 3t minus 5. So now we can use those two functions to do our integration, which will show up on our next page. So you can go ahead and take a look at the explanation up above, but based on what we talked about on the previous page, this is where we left off. And now we can just distribute the negatives through each of these to get negative 3t plus 5. And we can do each integral separately. We'll integrate from 0 to 5/3. That is that point on the x-axis, our vertex of our absolute value curve, of negative 3t plus 5, and then integrate from 5/3 to 3 of 3t minus 5. The work is shown here, giving us a solution of 41/6. All right, and now a little practice in working again with fundamental theorem of calculus part 1. So these are very similar to the ones we talked about at the beginning of class. And again, you're asked to differentiate each of these, so we're taking the derivative. So the solutions are now on the next page. So if g of x is the definite integral from negative 4 to x of e to the 2t cosine squared 1 minus 5t dt. That is just a direct application of fundamental theorem of calculus part 1. And g prime would be equal to this function with respect to x. So e to the 2x cosine squared 1 minus 5x. The next one is a little more interesting. A couple of other things have to happen here. First off, we have definite integral from x squared to 1. We're used to dealing with the constant being on the bottom and the function of x being on the top, so we want to switch the upper and lower limits by pulling out a negative in front. So that's what happens first right here. Then we need to remember we're taking the derivative of a composition of functions. And we'll take the derivative of the outside, which is the definite integral, times the derivative of the inside, where the inside is this x squared. So this negative sits out in front. In this example, they said go ahead and let u equal x squared to make it a little bit easier. So when we apply the derivative, we get u to the 4th plus 1 over u squared plus 1. Times the derivative of the inside, the derivative of u would be 2x. That's what we get here. And then we just need to remember to go back to be in terms of x. So we replace u with x squared. And that's what's going on here. So we get x squared to the fourth plus 1 over x squared squared plus 1 all times negative 2x. You don't have to write out this u substitution, but if it's helpful, you can do it that way. I just tend to think about this as evaluating our function f of t at x squared. So that would get me our negative out in front, and x squared so that would get me x squared to the fourth plus 1 over x squared squared plus 1 with the negative out in front. And then I think of taking the derivative of the inside, applying that chain rule, times the derivative of x squared, which is 2x. Which does give us the exact same answer that was shown down here. So if you like using the u and taking the derivative with respect to u times the derivative of the inside, you can certainly do that. Our final example is another fundamental theorem part 1. This time we have a function of x as the lower integration limit and the upper integration limit. But the procedure, we're still differentiating, we're taking the derivative. Procedure would still be the same. We'll evaluate this function at the upper integration limit, 3x, and then multiply by the derivative of the inside, which would be 3, minus this function evaluated at the square root of x, times the derivative of the inside, which would be 1/2 x to the negative 1/2. So let's go ahead and take a look at the solution. So here, it's written kind of in the backwards order, but here is where we are plugging in our 3x. So we have 3x squared times sine of 1 plus 3x squared times the derivative of the inside, which is 3, plus, now we're going to plug in the square root of x, so actually we are subtracting square root of x squared right here times the sine of 1 plus the square root of x squared times the derivative of the inside, which is 1/2 x to the negative 1/2. So the order is a little backwards from what you would expect, but we plug in 3x, and remember our chain rule here, and we subtract, plugging in square root of x, including the chain rule here. Alright, that should do it. Homework tonight should not take very long, about 20 to 25 minutes. 3 through 33 odd on page 306.